the number of worlds is
very big.
Very, very, very big. Where do those worlds fit? Where do they go?
The short answer is the worlds don't exist in space. Space exists separately in each world. So, I mean, there's a technical answer to your question, which is Hilbert space, the space of all possible quantum mechanical states. But physically, we want to put these worlds somewhere. That's just a wrong intuition that we have. There is no such thing as the physical spatial location of the worlds because space is inside the worlds.
One of the properties of this interpretation is that you can't travel from one world to the other.
That's right.
Which kind of makes you feel that they're existing separately.
They are existing separately and simultaneously.
Without
locations in space.
How is it possible to visualize them existing without a location in space?
The real answer to that, the honest answer, is the equations predict it.
Yeah.
If you can't visualize it, so much worse for you. The equations are crystal clear about what they're predicting.
Is there a way to get to the closer to understanding and visualizing the weirdness of the implications of this?
I don't think it's that hard. It wasn't that hard for me. I don't mind the idea that when I make a quantum mechanical measurement, there is later on in the universe multiple descendants of my present self who got different answers for that measurement. I can't interact with them. Hilbert space, the space of all quantum wave functions, was always big enough to include all of them. I'm going to worry about the parts of the universe I can observe. So let's put it this way. Many worlds comes about by taking the Schrdinger equation seriously. The Schrdinger equation was invented to fit the data, to fit the spectrum of different atoms and different, emission and absorption experiments. And it's perfectly legitimate to say, well, okay, you're taking the Schrdinger equation, you're extrapolating it. You're trusting it, believing it beyond what we can observe. I don't want to do that, right? That's perfectly legit, except, okay, then what do you believe? Come up with a better theory. You're saying you don't believe the Schrdinger equation. Tell me the equation that you believe in. Turns out, and people have done that, turns out it's super hard to do that in a legitimate way that fits the data.
And many worlds is a really clean.
Absolutely. The most austere, clean, no extra baggage theory of quantum mechanics.
But if it, in fact, is correct, isn't it the weirdest thing of anything we know?
Yes. In fact, let me put it this way. The single best reason, in my mind, to be skeptical about many worlds is not because it doesn't make sense or it doesn't fit the data or I don't know where the worlds are going or whatever. It's because to make that extrapolation, to take seriously the equation that we know is correct in other regimes, requires new philosophy, requires a new way of thinking about identity, about probability, about prediction, a whole bunch of things. It's work to do that philosophy, and I've been doing it, and others have done it, and I think it's very, very doable. But it's not straightforward. It's not a simple extrapolation from what we already know. It's a grand extrapolation very far away. And if you just wanted to be sort of methodologically conservative and say, that's a step too far, I don't want to buy it, I'm sympathetic to that. I think that you're just wimping out. I think that you should have more courage, but I get the impulse.
And there is, under many worlds, an era of time where if you rewind it back, there's going to be one initial state.
That's right. All of quantum mechanics, all different versions require a kind of arrow of time. It might be different in every kind, but the quantum measurement process is irreversible. You can measure something, it collapses, you can't go backwards. If someone tells you the outcome, if I say, I've measured an electron, its spin is clockwise, and they say, what was it before I measured it? You know there was some part of it that was clockwise, but you don't know how much, right? And many worlds is no different. But the nice thing is that the kind of arrow of time you need in many worlds is exactly the kind of arrow of time you need anyway for entropy and thermodynamics and so forth. You need a simple, low entropy initial state. That's what you need in both cases.